Cool. All right, I guess we can begin. Well, so I can run over a few things. I can do a quick recap. I'll only take 5-10 minutes to do that, and then I think we'll just handle specific questions. I like to run it more like a consultation rather than a this is what you should know, because if you want to know certain specific things, I can explain them in a different way. I mean, otherwise the lectures and the recorded material are the best way. But just to summarize, I don't know what most people here are for, I guess, quiz beforehand, I guess. You're interested in what's going to be there, or?
Sure, yeah.
Okay, cool. All right, I'll do a brief rundown. So this is not comprehensive, but some key things. So we'll do, okay, maybe if I need to do, thanks, Microsoft. So, oh, I like how this runs. So with op-amps, you have some non-idealities. So non-idealities. Oh, yikes. So let's just take, for example, a differential amplifier. So minus, plus, for example, here. So you have two inputs. So what are some of the problems we could have with this amplifier? Well, we have currents flowing in. So we have IB and IOS. So bias and offset currents. What else do we have? We have the finite gain bandwidth of the op-amp. So if anyone needs me to explain any of these, I'm going to gloss through them. I'm going to list them all out, and I assume you all know exactly what they mean. If you don't, just stop me. But with bias currents, you've got currents flowing into the amplifier because the input impedance is realistically not infinite. We assume it's infinite, but realistically it's not. So you have to be careful with that. Similarly, the amplifier won't have infinite bandwidth. So for a particular gain, you'll have a particular bandwidth. I can touch more on that in a bit. You'll also have PSRR, right? So power supply rejection ratio and common mode rejection ratio. You'll have things like the common mode input voltage, right? So these are to do with your ability to reject your power, the ability or the efficiency of the op-amp being able to reject your power supply or signals that are common present on both the inputs, as well as the absolute voltage range you can subject your inputs to. You also have offset voltage, so VOS. So there'll be like a little voltage source sitting inside the op-amp, so it's not physically, but equivalently input referred. There'll be a small offset voltage, which will introduce an error in any of your amplification measurements. So we're happy with all these terms here? So those are some of the important ones. There's obviously stuff like the open loop gain. So like a open loop, that's not infinite. Yeah. Okay. So happy with that? Cool. All right. So that's in terms of the basic non-idealities for op-amps that you'll need to know. There might be more. Oh yeah. Obviously, one of the more important ones as well is the the voltage range. So voltage output range. So that ties into the common mode input voltage. It's just the same thing, but for the output. So for example, your op-amp might be operating at ±5, but obviously you won't be able to swing to ±5. Cool, so that's all. All right, what else is there? I think that's it for op-amps. We can
power supply, rejection. Oh, you've got that one.
PSR, yeah.
Yeah.
Oh, okay. So there is, what else is there? I guess we can look at some noise sources. So the key thing to remember for noise is that your noise is your it's a sum of squares. So your Vn total would be like V squared 1 plus V squared 2, yada, 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 right? To V to the n squared, right? Now, each of these noise sources might be filtered or put through a transfer function. If that's the case, then you'd have your, say, your noise power spectral density, say, V1 squared times by the magnitude of your transfer function squared, right? Now, further to more, if you want to find the total noise, or the RMS noise, you'll need to integrate that across frequency. So you'd have Vn, let's take the square root of that, and you have the integral from 0 to 1 on T obs, I believe. Or is it infinity to T obs? Either or, but you'd have V1 squared in terms of F, magnitude of H, F, squared dF, right? So this is going to be, T obs is going to be really large, this is going to be really small, that's not going to converge, so that will be to infinity hertz, and this will be 1 on T obs. So, like this. Right, so you'll observe for some real, so you'll go to infinity frequency, eventually it will drop down to 0 because nothing can, nothing can extend to infinity hertz. And you say, okay, well, where do I go to? You could go to 0. That is possible to do the integral from 0 to infinity, but usually it works out better if you have any 1 on F components to make it a very small value. Otherwise, you end up trying to integrate something that doesn't converge. So, bad times. Cool. That's the summary of now noise. Where does the noise actually come from? Where does V of N actually come from? Well, you have resistors, right, which are 4K, T, R. You have current sources, so diodes in this case. That's 2QI. And so that involves transistors, so BJTs in this case, not MOSFETs. MOSFETs are more complicated. You have channel resistance, so channel noise plus the shot noise. The important part for a MOS device is that you have your noise sits to be, send me into the next dimension. It is some value of K on WLF, I think GM. Once you refer it to the input, it's GM plus, I think it's 4KT channel resistance. GM squared, I believe, think. Double check the lecture notes for that because that's a bit, it's an approximation, so they use different approximations. The important part here is to see the 1 on F part. The important part is the 1 on F. So this bit here. That's the really important part. So you'll see that if I showed you a noise plot like this, what component do we think that is? It doesn't change with frequency, so this would be like a resistor, right? If I showed you something that looked like this, what component would that be? Would be a resistor, because this part doesn't change. And then you'd also have some 1 on F component, so it would have to involve some sort of a MOSFET. So if you had an amplifier, right? And you say, okay, what type is this? Is this a BJT based or is this a MOSFET, a CMOS based amplifier? Most of the chances it's going to be CMOS based because you see 1 on F, right? So a little bit of a tricky question there. All right, so that's noise. What else? There's some digital logic stuff. So you'll have, your rise time, fall time. So just again to recap, rise time is the time taken for the signal to rise. Typically, you can use 10 to 90, 80 to 20. It depends. It's usually defined, but some people use 20% to 80%. So that's for the rise time. Similarly for the fall time. You'll also have propagation delay. So say, for example, the 50% mark from here to the 50% mark on here. This delta of time here, that's your propagation delay. Similarly, 50%, 50%. From here to here, that's your propagation delay there, right? So those are the 4 sort of measurements you need in a rise time and propagation delay for the falling and rising edges. They're important as well. For digital logic, there's two really key things that you need to remember. Don't mess this up. Greater than T propagation delay of your logic, T propagation delay of your memory elements from clock to Q plus the setup time. That's a T, sorry. Right, normally we just ignore this component here and we simplify it to saying T has the period has to be greater than the time it takes for the propagation delay of your logic plus the propagation delay of your flip-flop elements plus the setup time of your flip-flop elements, right? So that's an important criteria. That's number one. Number two is T plus delta plus 2 jitter. Has to be less than, oh, sorry, give me 1 second. I messed up. So that is plus T hold. Has to be less than your T PD. Now, I can't remember if you do you touch contamination delay?
I think so.
Never mind, ignore this exists. This doesn't matter for you. Okay, cool. Yep, that's all you need to know, right? So this here, so your propagation delay, the amount of time you run your clock, it has to be longer than the time it takes to go through your logic and to go through your memory elements and to have your memory elements set up. Does that make sense? So this will, let's say, oh, calculate the speed that this can work at. And usually they might say, okay, well, you'll have, for n logic gates, right, where each gate is 10 nanoseconds. So you have n times 10 plus one memory element, they say, for example. These will be fixed. So then you just solve for, like, you solve t for n, or you have a relationship between t and n, basically. Cool. Any questions about that? Oh, it's a bit tilted. Yeah, after a league game.
So what was the middle one? T, PD, CQ. That's the memory elements, is it?
This one here. So this is your combinational logic. So you'll get this from like your NAND gates or whatever, right? This is your flip-flops. So these are from your flip. Let's just say if we have a D flip-flop, right, and it's positive edge triggered, and Q.
Yeah.
Oh, I didn't mean to do Q bar. Instinctive. Sorry. We have Q. It's the delay between here and here, right? So it's the delay from the rising edge of this clock, right? So let's just say propagation delay from here to here, right? So it'd be this delay from here to here, right? And T setup is the setup time of the flip-flop that's just given. Setup time is the amount of time you have to be before the clock edge for the flip-flop to clock a valid data output. Right? Cool. Does that make sense?
Yep.
Cool. Okay, so that's digital logic, clocking, and timing. A brief over. Oh yeah, so a little bit on logic families. So did a little bit of noise, did a bit of op amp. So logic families. This is kind of extended from the digital logic stuff. You have TTL and CMOS. So TTL and C and versus. So it's good to know the differences. So TTL is usually transistor. Well, they're all transistor based. Should stop saying that. TTL is BJT based, right? Usually have different doping concentrations. So you can have Schottky based transistors, or I guess overdoped Zeners. But the point is that you'll have some sort of NPN or PNP transistor in there. CMOS are MOSFET based. The main thing to know is that the CMOS devices, they run on lower voltage. So CMOS is lower voltage. So you can conserve more power. So lower power. Because, say for example, your TTL gate draws a certain amount of current, and your CMOS gate draws the same current, right? They both draw, say, 10 milliamps. If one's lower voltage, it's going to dissipate lower power because P equals V times R. So low power, and they're usually faster. But because they're lower voltage, they're more prone to noise. So more prone to noise. TTL, I'm just going to go like this, it's a bit wonk. TTL, that is, so I should say more robust noise. And they're more so, I wouldn't say legacy, they're still used, but less so in this day and age because we're driving towards more lower power stuff. So you'd see normally lower voltage parts. So TTL is 5 volts. So you have, it's important to know about your, actually I'll touch on margins in a sec, but it's important to know that there isn't, so this is like the, like this will have like regular, so this would be 74 like LS. So that's low voltage Schottky as an attempt to get lower threshold voltages. Or lower power, sorry. But you can have CMOS, you can have different things like HC, you can have AUP, AUC. They all stand for different, the monikers for different logic styles. TI has a good guide on the different logic families. There's like 14 or 17 of them. Look at that in your own time because it is a good thing to look at. One more thing on logic is your thresholds. So say for example you have your say VCC and ground, usually 0 volts. You'll have what you call your input high and out, your input high, input low, output low. So you say you have V output high, V output low. These are the values that you have to satisfy to meet the conditions of the logic family. You'll have V input high and V input low. So V input low, V input high, right? So you need to be above this or below this to register an input low and an input high. This needs to be above this or this needs to be below this to be a valid output, right? Can you get me my sausage? Oi! Your noise margins are then the difference between these two. So your noise margin, your noise margin low is the gap between here, and your noise margin high is the gap between here. Yeah, is that cool? So it would be VOH minus VIH, and so yeah, it would be V output high minus V input high, and then this one would be V input low minus V output low. It's swapped because the levels they're flipped. Right? You always want to be below or above one and below the other, hence why they swap around. Cool, is that clear? So those are your margins. And then so this area in here is the forbidden region. You never ever want to go in this region, otherwise disasters can happen. You'll have gates the states that aren't defined. You'll be in a metastable state. You might not get a 1 or a 0, or you'll get both, or you'll get neither. It depends. I don't know. Okay. Cool. Sorry, just got an email from Jeff. Okay. So that's all good? Cool. So that's a quick primer on the digital logic stuff. What else is missing? What else did you cover? I can't remember the course outline.
I think that was the majority of the digital. Can anyone remember?
No, I just meant in general too. Like I mean, we're in week 4, week 3 now. So what other content is there?
Esd Protection.
Good. Esd Protection. Right. Okay. So I touched on op amps, noise, digital logic. So we can look a bit about ESD now. So ESD is electrostatic discharge. So I'm not going to write it. It's too much text. But electrostatic discharge. So there are different methods of doing it, of implementing ESD protection. So protection. So this is important because usually for CMOS devices, they're made of very sensitive, thin oxide layers in the actual transistors, the MOSFETs, that can easily blow up with say, static electricity or a high energy event. So you want to protect for that. So you can use this, there's a lot of common you can put some, you might put this is optional. This is optional, but what you'll have is, you'll have something that will look like at least something like this. And this will go off into, like I say, a transistor or something like that. Smooth brain me. There we go. There you go, for example, right? So this would be VCC, and this would be ground. So what this does is it protects you if you exceed VCC. Say you get an 1,000 volt spike, right? It doesn't damage this oxide. What it does is that the energy will go up into the VCC rail. Conversely, if you go negative, it'll flow that way, flow of electron, charge that way, forward biased. So that's for your inputs. For your outputs, you really have two sort of options. You can do the same thing, right? So let's just say you have some sort of a transistor. I shouldn't draw that. Let's just say you have some sort of like a MOSFET output stage that looks like this. NMOS. So it goes to ground, supply. You can do a very similar thing. So you can go basically exactly identical, same configuration. So your output, happy days. That works good. Now there's also another option, or two other things to consider, is you can get ESD events from inputs to outputs, inputs to inputs, outputs to outputs, supply to inputs, supply, every single permutation and combination between your power supply, your ground, your inputs, and your outputs. Current can flow any direction through any of those. So to remedy that, you can usually you put some Esd protection across your supply, which you'll use a Zener diode of some kind. So that will work. This will be in conjunction with your inputs and your outputs. So you'll always see something like this in conjunction with your other remaining Esd protection methods. Now, you can, what do you call it? You can use different methods for open drain. So you need to be a bit careful with open drain, say, or open collector. Say your output stage looks like this. So this is your output terminal. This goes blah, 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 somewhere in your gate, right? Okay, that's a bit more than ground, but sure. So it goes like that. So you can do the same thing. So you can use option A, or option number 1, as we've seen before, and we can just throw diodes sort of like this, right? So this is open drain output. You can do something like this, right? But that's not very good, because if you want this voltage, if you want to level shift or pull up to a different domain, you'll end up forward biasing this diode here, which is not good. So instead, something that's slightly better. Again, they have their own benefits and drawbacks. Again, what's slightly better is if you use a Zener diode. There, right? And you dope your Zener diode in such a way you get the reverse breakdown voltage that you want. All right, cool. Any questions about that? So,
do we need to know how that works, or like just
how a Zener diode works?
Well, no, like how putting it there is a better choice than.
Yeah, okay, I can explain that. So your forward voltages will be typically the same. So the bottom diode, let's just say this is A and this is B. The bottom diode in A will be basically almost similar to what's in B. Your forward voltage might change a little bit. It will change a little bit, but it's mostly the same. In A, you're limited by VCC. With B, you're not limited by VCC. Now, if your transistor is rated for voltages only greater than VCC, less than VCC. So let's just say, for example, if VCC is 5 volts and I've designed this transistor such as that anything more than 5, that it will physically explode, then this is a viable strategy, right? Because I can't put more than 5 volts anyway. Otherwise, it will damage itself. 5 volts plus a voltage drop of the diode, so 5.6 volts-ish, 5.7. This method is good because I can tune this reverse breakdown voltage of this Zener to be whatever I want. It could be 5.6, it could be 70, it could be 56, it could be 47. It depends on what you design it to be. So that means I can level shift up to a domain that is at least that high. Well, at most that high, I should say. Why would you not always do B instead of A? Well, it's a lot more difficult to actually construct a Zener than a normal diode because of the doping concentrations. When you produce some logic families, this is slightly out of the scope, but when you buy a chip as a chip manufacturer, like say I've designed it as my integrated circuit, I send it off to get made, it comes with like a base layer or a base package, which is just transistors and metal. If I want fancier devices, like a Zener is technically a fancy device, I have to pay extra. And I might not want to pay extra. It might cost me an extra $37,000, right? And I don't want to pay that for the extra mask kit. But anyway, the point is that there are two viable streams. So a common question is drawing ESD current paths during ESD events. So be across that. I think there was a specific example or question in one of the past papers. But yeah, okay. I think, is there anything else?
Would you maybe mind showing us how the current path might go for, because you said it could be between power supply, ground inputs or outputs. Would we be asked to draw any of the, like between input and output, where would it go between?
Yeah.
Yeah. Maybe just a really simple.
Yep,
chip.
really simple,
Yeah.
an inverter.
Yeah.
So this goes in. So this is an inverter. Again, excuse the drawing, I'm trying to speed draw it. So again, went to an art school, but that was a good minute ago. You can tell I got into dance and not art.
We might have to see a rendition later.
No, I don't do interpretive dance. Okay. So this is what a typical basic inverter, what an ESD structure would look like. Let's just say we get a positive pulse. So we get like a massive positive spike there. What would happen is I flow in, where would it flow? Up. Now we have two diodes here, a regular diode and a Zener diode. Now, Zener diodes, as I mentioned, they're designed to break down at a certain voltage. Typically a lot less than a regular diode. So where would it flow? In this branch, the branch 1 or 2? This branch here or this branch here? Branch 2? And then let's just say we wanted to go to ground. We're already at ground, right? But if we wanted to flow to the output, if it was ground, we're at ground. But what if it was to the output? Where would it flow?
That diode that you're on.
Up.
Yeah.
There you go. That's how you get from input to output. Conversely, if you were to get from output to input, you'd go through here, you'd break down, you'd go up like that and like that. Right?
Yeah.
Supply to supply is pretty simple. That's just through the Zener here. Like that. Right? So there's a really basic example of ESD paths.
Yeah, fairly straightforward then.
Yeah, so the idea is that you trace the direction of the diodes. You just follow the diodes. That's all you have to do. And for a Zener, you can easily reverse break that down. So it's okay to go in the opposite direction of a Zener. Granted, it's constructed correctly, but here we have to assume it is. Cool. Is there any other like content that I'm missing? I think that's a good.
Yeah, that was awesome. Thanks so much, Billy.
Mm-hmm.
There was a bit in like slew rate.
Oh yeah, so dashing back up to the op-amp stuff.
Distortion stuff.
Yeah, so that's a good point. I'm just going to return all the way up to the op-amp. Yeah, so there's also up here. Sorry about being too disjointed. Yeah.
Maybe bandwidth. Like how do you work with open loop and closed loop and gain bandwidth products?
Yeah.
Sorts of things
Yeah, sure. I can elaborate a bit more on that. So the slew rate. So Usually if you deal, okay, just to expand a bit more on the op-amp stuff because I rushed through it. So usually with errors, right? Actually, let me just circle it like this. So usually with errors, so voltage offset and the input bias and offset current, you can draw them as different voltage or current sources around in the circuit, and you'll just you could do superposition or you can do KCL all at once. I'd recommend doing superposition. You just see the output voltage with respect to each of the different sources. So like, how does VLS change the output voltage? How does IB and IOS change the output voltage, right? So you'll look at those. That will get you your total output voltage, and superposition, you can just add them all together. PSR, CMR, they're a bit more difficult, at least mathematically. Now, open loop bandwidth, slew rate, gain bandwidth. I can show you, we'll touch on that a bit more actually now because we can mathematically really simply show that. So slew rate is the fastest your op-amp output can change. So say for example you have, let's just keep it simple, a square wave, right? The output is going to look like, it'll look like something like this, right? Because it can only, the gradient of the output can only change so much. And it will be different for your slew rate, your positive slew rate and your negative slew rate. They should be identical, but they'll be different, and that's due to the internal construction of the op-amp. Some of them will be the same, some of them won't be. It depends. There's probably, like, off the top of my head, at least 10,000 different op-amps available on the market. So no, I'm not going to find you one that is symmetric or an example of asymmetric. I encourage you to do it yourself on DigiKey if you feel so enticed to do so. But the point is that with your slew rate, you know, let's just say, even more simple than a square wave, we have, say, a sine wave or a cosine wave. We know that VO is equal to A cos 2 pi ft, right? And if we take the derivative of the signal, and we want to see when it's max. So we want to see when it's a maximum value. So that's when cos is 1, right? When the result of cos is 1. So then that's going to, and you take the derivative, that's going to be A 2 pi f. And because this term here, this will go to 1. So it's just 2 pi times f. That's equal to your slew rate. Right? So say if your slew rate was 1 volt per microsecond or 1 volt per second, make sure you get your units right. So if the slew rate, say 1 volts per second, and my frequency was like a kilohertz, I could solve for my maximum amplitude, right? So A in this case is oh, sheesh. A in this case is your amplitude, right? So this would be A, right? Because it's a cosine wave, so it goes to positive and negative of A. So that would be your amplitude. Cool. So if you have your peak to peak value, it would just be VPP on 2. So it would be V peak to peak times pi times F. Cool. So that's your slew rate. For your gain bandwidth, we assume that the gain bandwidth of the system is a straight line. So you have your open loop gain and your frequency. You assume that your gain bandwidth looks like that, right? That's a straight line. So for a particular closed loop gain, say if I close my gain to say, let's just say 100, and my A open loop, so this point up here is AOL, say 1E6, right? 1 times 10 to the 6, for example. What I'm going to have is intuitively, if I close the gain, my gain is going to look like this now, right? But what's my bandwidth going to look like? Is my bandwidth going to go off to infinity? Well, no, it's going to look like this now, right? So I'm going to get effectively more bandwidth. Say if I had ACL is equal to, say, 1,000. Again, this is just a cartoon, so it's not totally accurate. It would look like that. So you can see the bandwidth effectively. My 3 dB point of something with higher gain has less bandwidth than something that has lower gain has more bandwidth, right? So that's roughly how you approximate the gain bandwidth product. Sorry about that. Someone was having a stroke. Okay. Yeah. So how do you describe this? Well, usually you just say gain bandwidth is equal to your gain times bandwidth. Now, to get this slope, that's an integrator. So in the Laplacian domain, that's just divided by S. More appropriately, a better model would be a single pole model. So realistically, what you would look like, what you'd have is something like, it's not a straight line, but something that looks like this, right? So this would still be AOL. This would be about maybe 10 hertz or something like that, right? So basically this bit up here would flatten. And all I'm saying is that this sharp, this perfect straight line is unrealistic. It more realistically look like that, right? So that can be described as a single pole model. So I'm just going to call it K on S plus pole 1, right? Even more realistically, if you remember, you'll have, this would actually be a second order system, right? So you'd have K on S plus 1, or P1, S plus P2, right? So you have a second order system. Now that's certainly a lot more detailed, but you can really just take a linear approximation. The gain bandwidth product is the gain times the bandwidth. It's a good enough approximation, depending on what you need to do. Sometimes it's not, and it's can be pretty bad if you're doing a linear approximation, but most general purpose cases you can do a linear approximation.
And bandwidth here is just meaning like literally the frequency at which
your 3 dB point.
Your 3
right?
dB.
So these corners here are your 3 dB points. Now, the general form you get, so this is a open loop of S, right? A open loop of S. These are just increasingly more complicated models. Sometimes there might even you might even have a 0 up here, so S plus Z1, right? You'd have a 0. It depends, but they're all related with the fact that your closed loop gain is your open loop gain 1 plus AOL times your feedback factor beta. Now, that's not the transistor beta, that's just a parameter beta. We just use it in that equation. You can see that if AOL is sufficiently large, you just get, so AOL beta is much greater than 1. You get AOL on AOL beta, and these just cancel out, so you get 1 on beta, right? And beta will be your feedback factor. So most amplifiers, say for an inverting or a non-inverting amp, you'll have say, so this voltage divider here forms your beta term, right? But again, this is a bit out of the scope of the course, just intuition and understanding on where it actually comes from, how this thing decreases. So basically you have this AOL value here, or sometimes a function itself, not just a value. Here we're assuming it's like this is just some constant, right? We ignore this S, we assume it's a straight line, this is just some constant. We plug that constant into when we need to find the bandwidth. It's just a linear approximation, but sometimes we can get more complicated and start plugging in. You know, this might be dependent on the op-ramp forward gain will be dependent on frequency, and your feedback factor will be dependent on frequency. All right, what else is there? There is PSR, CMR. Just quickly talking about your 2 quick things, and then we can throw it to some extra questions. So PSRR, again, is your, so let's just say you have some sort of an amplifier, right? It's your, again, fairly simple. Let's just say this is a value of A. It could be this circuit here, but let's just say it's some amplifier that has a gain, so A of F, right? So your power supply rejection ratio is how good the forward gain is compared to the power supply gain. So this is AVPS, AVF, forward gain, and in terms of, I'll use S, because Laplacian domain is the best. Right, so you have a power supply gain and you have a forward gain. So your PSRR in log is 20 log 10 of your forward gain. So what this is, let's just write this out. So your AVPS is your it would be your output divided by your input. So your output is VO divided by your input, which is just say V plus. Let's just say this is V plus. Right? So that's your output divided by your input. Your forward gain is just VO divided by VI. Right? Gain formula. Yeah, output divided by input. Right? So your power supply rejection ratio, we want to find VO on V plus. Right? So what we do is we invert AVPS. So AVPS to the power of -1, function of S is equal to V plus on VO. Right? We see that? It's just flipping this fraction. So if we times AVF times the inverse of AVPS, we get VO. So let me just do this. So AVF of S times by AVPS of S. That comes to 20 log 10. Probably shouldn't have done the log first. So this is, so to the -1. So this is VO on VI times, so I'm going to omit the S just for now, so it's faster from right. V plus on VO, right? The VOs cancel, and we get 20 log 10 of V plus on VI. So we're seeing how much does the ratio of how much our power supply affects the input. Yeah, I did that right? AVPS minus. Yeah, that's right. Yeah, that's right. And so this will be dependent on frequency. So just function of S, right? But practically we can't actually measure VI in most cases if our input is grounded. It'll just always be 0. But yeah, this might, ideally you want your denominator to be very small and your numerator to be very small and your denominator to be very large. This number will be negative, right? Because you've got log of something less than 1. But that's fine. You just take the magnitude. You'll get like minus whatever dB. So there'll be minus dB attenuation. So it's just the opposite of that, which is just, say if it was minus 80, you'd have 80.
And what sort of question might we get about, would we have to calculate PSRR?
Yeah, you might be given like
a graph of PSRR?
Yeah, like they might ask you to do a general, I don't know. It could be, the thing about these quizzes is that they're so ad hoc and arbitrary. As long as I can tell you there'll be an op-ed. You might be asked to calculate the general trend of PSRR. You might be asked to get the general trend of, or to calculate the specific value, find the PSRR value, or work backwards. If you have a noisy supply and a PSRR of, say, 70 dB, calculate the output ripple, right? And it's just using this formula. Right. Now, so just to elaborate on that, this value here will look like that, right? It'll go down with gain, right? Because your amplifier has a certain bandwidth, right? So again, it's literally just this thing here when you close the bandwidth. Conversely, your power supply, this value here, your power supply to your output will do something like this. It'll get worse with an increase in frequency, right? So if you look at the ratio between here and here, it's very large. But if you look at the ratio between like here and here, it's very, very small, right? Which is bad. Cool. Clear on that. I want to do a little interactive thing briefly before I throw it to a couple of questions. We'll do a nasty question. So we have 2 amplifiers, right? All right. So we can assume that there's no bias currents and whatever and whatnot. So let me just draw 2 op-amp configurations. All right. this one here. Nothing scary yet. What's the top configuration? 3, 2, 1.
Inverting.
Wrong.
Not inverting.
Yeah. What's the bottom one?
Inverting.
All right.
What's the answer to
Good. 50-50 chance. And then one was wrong, 100%. All right. Redemption time. Which one has superior common mode input voltage? Let's take a guess. 50-50 chance. Which one has better common mode input voltage? 50-50. Come on. Who wants to take the gamble?
Go Jack.
I have no idea. Inverting.
Inverting.
Wow, you got that one right.
Yeah.
Why is that? Think about it. Now, assume that the bandwidth isn't an issue, the offsets are not existent, right? We only have to deal with common mode input range. So that's the range that both the inputs can't exceed. So common mode means average between the two. So differential means the inverse or opposite, or the subtraction of the two. So differential, so let's just say AD is, or no, so I should say voltage of the differential is, say, your V plus node minus your V minus node, right? Your V common mode would be your V plus your V minus on 2, your average between the two, right? So common mode is the average between the two, differential is the difference between the two. You said one of them has better common mode performance. Why is that? What's the value? So if this is V in.
Yeah, there's a resistor in the way, right?
Sort of, you're close. What's the value of this voltage here? Yeah. Now, if the op-amp's operating perfectly, it's not slew rate limited, it's not bandwidth limited, what's the voltage here at the negative pin, the inverting pin? Yeah, so what would it be?
So V, what was that, VN?
Yeah, VN. Yeah, perfect. Exactly correct. Yeah, so it'd be VN. Okay, let's continue. What's the voltage here at this plus pin?
0.
Yep. So what would the voltage be here?
0.
Right. So what can we deduce? What's the common mode voltage if I put 5 volts here? What's the average voltage between the inputs if I put 5 volts for V in? 0. If I put 10 volts?
0.
Assuming the op-amp power supplies are, let's just say, plus minus 25. If I put like 20, still be, assuming it's rail-to-rail input and rail-to-rail output, still be 0, right? What about here? What if I put 5 volts here? What's the common mode voltage across the inputs? 5. 5 plus 5 is 10, divided by 2 is 5. Yeah, if I put 10, it's, yeah, exactly. So which would have better common mode input performance? The inverting or non-inverting? Non-inverting or inverting, sorry.
Is it better to have a high voltage?
No.
No, okay.
Because what could happen is that you know this is well defined. Say this is plus and minus. This is minus VSS or just VSS, and this is V. Oh, I did it right. VDD. Okay, VDD and VSS. Right. Let's just say it's did it again. Let's just say it's a dual rail. Right. You got a plus and minus voltage. Assuming the op-amp's working fine, your common mode voltage, it's always going to be 0, right? Now, if VDD and VSS is plus minus 5, and you put 3200 volts on here, obviously a lot of current's going to flow. This op-amp's not going to keep up, and the voltage is going to start rising, right? But assuming it's working perfectly, this op-amp, the inverting one, will have obviously the better common mode because it's well defined as like, okay, assuming I'm not overvolting it, it's always 0. This one is like, well, maybe it depends. Now, why is that an issue? Because your open loop, your op-amp, so this is your open loop gain, the magnitude, and this is the VCM, right? So say, for example, we wanted to plot your common mode voltage versus your open loop gain, right? Why is this important? Well, if this, let's just say this is VCM, let's just say at this point it's VSS, so let's just say minus 5. And this is VDD. This is 5 and this is 0, right? So if this is always 0, I know my AOL is going to be, let's just say here, I know it's like very large, 10 to the 6 or something, right? On happy days, I know my open loop game is always going to be this. It's never going to change, right? But this one, when I start wandering with my common mode voltage, what actually happens is this. When the voltage gets too close to the rails, as you saw in the labs, the op-amp starts to turn off, right? It can't swing all the way to the positive. It can't swing all the way to the negative. It's because the op-amp turns off. When the op-amp starts to turn off, you lose open loop gain. And when you start losing open loop gain, remember I made this assumption where the value is really big. It's no longer really big. The op-amp stops. You lose accuracy, right? So, tricky question there. All right. Anyone have anything else specific? No?
Maybe
Quiz question?
Ask online people.
fan out.
Fan out. Okay. Yeah, all right. So let's go back to digital logic. So there's there's fan out / in, right? So what that is, it's basically it's how much current or how well we can drive logic gates. So say for example if we have a logic gate here, right? Now, how many logic gates can we drive with that? That's the fan out, right? Fan in isn't used as much, but it's the opposite, I believe. So fan out is how many gates we can load and output. Fan in is how many inputs gates you can load with the input. Looking from the other perspective, right? So how many it's basically just focus on fan out. That's what you'll mostly get asked about. Usually you'll get mostly asked about fan out. So basically, say for example, if my maximum current for a high value is say 20 milliamps flowing out, right? And I have just a whole bunch of inverters, say for example, keeping it simple. And each inverter, so I input high is a milliamp. When the input is high, it draws a milliamp, and the output is low, or the output is high, it's driving, this drives 20 milliamps when the output is high, this sucks in 1 milliamp when the input is high. How many inverters can I have attached? 20. It's that simple. Yeah. Now, there is something more complicated when it comes to propagation delays. Inside these gates, equivalently, your input to your gate will look like, electrically, it'll look like this. There won't be physical components like this, might be, but it can be boiled down to an equivalent of this, right? An RC low pass or an RC network, right? So what will happen is that when you put in a value, what you'll have is, I should say, let me just erase this so it's drawn correctly. So you'd have capacitive loading from these gates, and you'd have the finite output resistance of the logic driver, right? So inside here, you either have a resistor tying to the power supply to the output, or a resistor to the ground tying to the output. So it's like having a switch, right? Right, so I can either switch in a resistor to the power supply or switch in a resistor to ground, right? So you have a resistor. Let's just say this is a CMOS gate, right? So looking into here, you'll have like an inverter, right? You'll have a CMOS inverter, right? Which looks like that, tied together, right? The equivalent circuit, if you look into a MOSFET here, this just looks like a capacitor, right? And so these will combine in parallel. So you'll have some sort of equivalent capacitance, again, out of the scope, but you'll have a capacitance from this here, that there. So that's where this capacitance down here comes from. That's where this capacitance comes from. And you'll have this internal resistance, which is where this internal resistor comes from. So I'd use the rainbow pen. Worked out a lot worse than I expected. No, that wasn't the rainbow. That was a glitter pen. Oh, it's the rainbow pen. But yeah, so you'll have some sort of equivalent time constant from the gate input capacitance. So a typical question would be you have you have a logic IC, you have an ADC. Again, this is more like a final exam question. They'll give you a data sheet and they'll be like, okay, here's an analog to digital converter that uses I2C. You need to drive the lines with this sort of data rate, right? You can see, actually no, it would just say this sort of data rate. Like we need to run the ADC data bus at like 100 kilohertz, right? Calculate the value of the pull-up resistors. You'll have to go in, look at the data sheet, find the equivalent input capacitance values, find the speed you want to run it at, which is typically given, and then you'll calculate R. Right? A useful thing to note is that your propagation delay, bro, am I trolling?
Not working.
Nope, hold on. Do I need to press the button here? Bro.
No.
Nope, it's not working.
Sorry,
Do I need to press the button? Nope.
do you want to try another pen or something?
Oh no, I was just dragging my hand. For some reason, I was checking my hand. Okay, so T doesn't have touch reject? Boo. So your propagation delay is equal to your time constant, right? Which is R times C. But that's not the delay, that's your time constant. So typically your 50 to 50% is, or your 50% mark, I should say, not 50 to 50, is ln2 RC. So that's your propagation delay from, that's to like 50%. So if you want to see if something is charged 50%, if you want to see something that's charged, so that's TBD 50 and TPD 90, you can approximate as L. I believe it's not a G, it's not a G. RC. That's also for 90%. All right, cool. All right, but usually they'll like, okay, when does your output change from high to low? You want the 50% mark. Good, it's a good approximation. So you make sure you put the ln2 in there and you don't forget that. Otherwise, you're in for a very unfortunate time. Cool. Any other questions?
Did anyone have any questions or anyone online?
I've been looking at the chat. No one's having any questions online.
Oh, someone asked something.
Oh, there we go.
All right. What's the question?
They've asked about question 2A in the 2021 quiz. Might get
Oh, good lord. Okay.
But they've said, why a symmetrical clipped sinusoidal input does not have even harmonics?
Oh, okay. So this is a 2, 1, 3, 4 question. Okay. So basically, what's saying it's saying that I'll just draw it here. If you have a sine wave, right, that's symmetrically clipped, so or cosine wave, doesn't matter about the phase offset. So, something that looks like that, roughly, right? Very poorly symmetric, but symmetric. You're going to get, if it's a perfect sine wave, you're going to get one tone at F, right? But if you have a square wave, right? If you have a perfect square wave, you have something that looks like this, right? So a perfect square wave just looks like that, right? Now, hear me out. This time between here, T1, and T2, those are symmetrical, right? The same amount of high time, you have a duty cycle of 50%. The same amount of time that's high is the same amount of time that's low. Now, if you have a sine wave or a cosine wave, and we start to clip it, right, symmetrically, that means that what's going to happen is eventually it's going to start looking square, right? It's going to start looking like this, right? Oh, this is not a very good example. But my point is that when you start clipping it, your edges are going to start becoming vertical, and eventually what you'll get is you'll just get a perfect square wave, right? If you clip a sine wave so much, because each cycle of the up cycle and the down cycle, it's the same amount of time, and you just increase the gradients and it's clipped by the same amount, your duty cycle will be 50%, same as a regular square wave, right? Now, why does a square wave have only odd harmonics? Well, revise your Fourier series, but for every coefficient, the amplitude decreases by 1 on n squared, and you have 2n, your frequencies at like 2n plus 1, your odd harmonics, right? So you have 3, right? So like 3, 5, 7, 9, that sort of stuff, right? And it would decrease by 1 on n squared every time you go. It's kind of squared. It's square. Yeah, it kind of looks like a parabola, I guess. Like, so something like that. So it actually be like that. Kind of look like that. Yeah. It's more exponential, but you get the idea. The general trend is squared, right? So 1 on n squared. Yeah.
Hopefully that answered Qinglong's question. Anyone else got any questions for Julia or anyone online?
So if it was asymmetrically flipped, you'll have even harmonics as well, because what you've got now is something that'll look like that. Oops. That. So obviously it's not even, you're not, when you do the Fourier series and you integrate, the times aren't even, so your even component is no longer 0. But when you do your Fourier series, your even component 0, if it's symmetric. Right. Is that right? I think if it's even symmetric, it's even, then the plus is still 0, if I remember correctly.
I had some questions, Julian, about level shifting and driving transmission lines as well.
Okay.
There were a few things that we covered that may not be as.
So, perfect. Back down to the digital logic. So level shifting is, we need to do it because so say for example, you've got 2 different domains, right? So let's just say your VCC1 is here, and okay, just vanish. VCC2 is here. Let's just say this is V output high, V output low. This is V. Oh, I should not do that. V input low. I'll just draw it up here to be more clear. And V input high. Now, if we have a 0 on the output here, so we flow into where there's V input low. We're happy days. If we have a V output high here, well, if this is our forbidden region for this logic gate, and this is our forbidden region for this logic gate, we're in our forbidden region, right? It won't work. So we need to shift this level up to here. So the most basic way of doing it is to use well, what do we need to do to the signal? Do we need to attenuate, make it smaller, or amplify, make it larger?
Go bump it up so it's there.
Which is?
Amplifier.
Yep, cool. So we need some sort of an amplifier. The most basic amplifier we can make is if you remember from 2133, a common emitter. Right? So if we put this here, and I'm able to draw, not like an absolute ape. Common emitter, right? We don't care about the specific biasing because we just care about it being on and off. So this is just a very high gain amplifier, basically. So if you put a 0, you get a 1. If you put a 1, you get a 0. It's an inverting amplifier. Right? Now, this so this voltage across here has to be greater than a VBE, right? A threshold. Your B has to be greater than the VBE threshold, right? So typically about 0.6, 0.7, 0.6, right? Can change, it depends. So that needs to be greater than 0.6. You'll need a certain amount of current going to the base to forward bias it. Probably 10, 20 microamps, something very small. It depends on the transistor and the beta, so just say 20 microamps, reasonable value, right? So depending if this resistor is 1K, and this needs to be 0.6 volts, 20 microamps times 1K is, wait, my brain's lagging, 10 to 36.
20 mil.
Yeah. Sorry, what was that?
20 milli.
20 millivolts. Yeah, sorry. 3, 6, 2, yeah, 20. So this would need to be, you know, you need to be greater than 620 millivolts on here to get a high, to get the transistor to turn on, right? And then you'll have the output, which will give, say, VCC2, right? So that's the second domain up here. So this will shift all the way. This will then take this and do the shifting for you here, but it will be inverted. So you gotta. This is just like doing an inverter, but with an open drain. Well, in this case, it's an open collector, not a drain, because it's a BJT. One thing to note is that similarly to note, this will also affect your propagation times as well. So say, for example, you're connecting to a whole bunch of gates here. It's like putting a capacitor. You'll have a charge up time between RL and CL. All right, cool. All right, does that answer your question about level shifting a little? There are more advanced ways of level shifting, but this is sufficient.
Sure. And would we need to do another inverter to then?
If you want to uninvert it, then yeah, or you just change your logic on the outside.
Yeah.
You just redesign your system. Or if you want it to be non-inverting, then yeah, you can just feed it into another, just same thing, just another amplifier like this. There you go, just like that. Obviously, this CL won't exist anymore because it's sitting inside the, thank you, Microsoft, the amplifier. There you go. So yeah, that would be a net non-inverting amplifier. Yeah, so you got 2 inverting stages. That's just like doing 2 inverters like that.
And I guess transmission lines, what sort of, like, there's a lot of maths going on with those.
So to do transmission lines properly, you need to start doing, worrying about, if you want to do it analytically, you need to deal with the telegraphist equations, right?
Sure.
So you need to start, you need to write, basically, I believe it's like a Helmholtz oscillator from your your infinitesimally small short like transmission line model. Right. Remember, so it's like if you have a transmission line and you boil it down, you get something that looks like this, right? Like this, and some shunt conductance in there.
I don't know if we've seen that one yet. All we really seem to look at was like that. Reflections.
Yeah, so one of the reasons why you get reflections is partly because of this. But what you'll have is, so if you have a generator, let's just say you have a data transmission line, and you have a generator and a receiver, right? Now, let's just say this generator has, for example, 50 ohms worth of, let me draw a lot larger, just give me a sec. Better if I draw it larger, got all the space. Right, now what if I draw these 2 amplifiers, right? Let's just say this is your transmission line, right? So this looking into here is approximately infinity, right? It's an ideal amplifier, your input impedance is infinity. Looking into here is 0, because the ideal amplifier, your output impedance is 0, right? Now, what you need to know about is you have some sort of propagation velocity, right? So your propagation velocity through your coax is the speed of light times some like velocity factor. Could be the square root of your, oh my lord, I can't write epsilon to save my actual life. That looks nice. So it could be the speed of light on square root of your dielectric constant, relative dielectric constant. It could be, you'll have some sort of, it could be the speed of light. Who knows? It could be, you might say it's like, 0.6 C or something. So you know that V, your velocity, so your speed, is lambda F, right? So you know that generally when you have to start worrying about things being a transmission line is anywhere, if your F max, so your F So you'll have a physical, or I'm trying to think how to make this not really complicated. So you have technically the electrical length, but let's just say the physical length. What you'll have is you want to make sure that your wavelength of your signal is 1/10 of the electrical length of the line. So what that means is that you'll have some sort of maximum frequency, right? That is equal to, say for example, you want this to be, so you want this to be, I shouldn't do it in, actually, this is better. Let me just do it this way. So you'll have VP equals F lambda, right? So you want, trying to think of a good example. Say, for example, you want to know what the maximum frequency your line can handle, or the maximum rise time, right? You would want to know, you'd have V, you'd have VP, and you'd have your wavelength, right? Which would, in this case, you don't want your frequency to be more than 1/10 or 15 of the wavelength, right? So basically what's saying is you want this length here, so L has to be less or equal to roughly, 1/10 of lambda, right? So your wavelength, you want your line to be 10 times shorter than, let's just say your wave is this long, right? You want your transmission line or your whatever you want to be 10 times as short, right? Before you have to worry about impedance matching. Because let's just say it's 10 times longer, what can happen is that if you have a wavelength and you have multiple wavelengths, these wavelengths can reflect and get constructive and deconstructive interference, right? So you'll say anywhere between L is less than or equal to a 10 or a 15. It depends. It's all sort of an art rather than a science. So now that we know that lambda, L has to be effectively, let's just say L is equal to 1/10 of lambda, right? We know that lambda is L equals 10L equals lambda, right? So then we can just plug that into there, and then we have VP F max 10 lambda, right? Or 10L, sorry, 10L, not 10 lambda, 10L, right? So L is the length of this line here, right? And say, for example, we're talking about the rise time. Another thing you should know is that just basic identity based off the exponential function is 0.35, that, right? So the bandwidth is 0.35 times the rise time. So this is like saying F max because you assume it's from DC. So then you combine 1 and 2. So then you get 2 into 1. After rearranging, you then get VP equals 0.35 on T rise times 10L, right? So say, for example, you know your propagation speed, you know your rise time. Let's just say it's a 1 nanosecond rise time, and the speed of light propagating through the coax is 0.6 times C, 0.6 times speed of light. You have TR, you have VP, you can calculate the length, the maximum length, before you start to worry about impedance matching. Now, let's just say you do want to worry about impedance matching. Again, this is like an insane oversimplification. If anyone saw me do this, I'd get like actually decapitated. If you have a high impedance, your wave will reflect back perfectly, right? With a phase of 1 and an amplitude of 1. So it would reflect back perfectly. If you had a short circuit, it would reflect back perfectly, but with a flipped phase, right? So what will happen is if I launch a wave here, it's going to reflect back with the same phase, and it hits here. This is like a short circuit, right? It will reflect back with a -1 phase, and then a +1, and then a -1, and then a +1, and then a -1. It's going to keep bouncing back and forward forever. How do we get rid of this? Well, we terminate the generator with some impedance. So let's say like 33 ohms. Or ideally it should be Z0. Okay. Ideally the generator output should be 50 ohms. So looking into here, it should be now 50 ohms. So if you have a generator, right, perfect ideal generator, you should have 50 ohms, right? Or let's just say the transmission line is 50 ohms, you'd put 50 ohms there. If it's 75, you put 75 or whatever, so you impedance match. You could do the same thing on the input as well. You'd put like 50 ohms to ground, right? So like you'd put Z0 to ground. So Z0 is a characteristic impedance of the transmission line. This is encouraging way more in the EMAG theory. But in RF, this is like
we walked the line, I think, between.
Yeah. To really understand this, you need to do 4604.
Yeah.
You have to do 4604 to understand this. But the key point is that you'll have this, right? You'll have some sort of your signal will go through your medium at a certain speed, and to maintain that relationship, you'll have a wavelength for a certain frequency, and you have to abide by either of these rules. You can choose. I think Torsten says 10. I like to use 15 because I'm scared. But you want your length of your transmission line, or your trace, or your PCB track, or your cable, or whatever, twisted pair to be generally less than 1 on 15 or 1 on 10, and then you have to worry about absolutely none of this. It's only when it starts getting really large that you have to start worrying about impedance matching. All right, so say for example, if I launch in a step, right, out of here, right, I'd get a step reflected back this way. I'd get a step reflected back this way. So same thing, but just traversing this way. And then it hits say this is 0 ohms. It's not. It would actually flip to be negative now. And then I'd also get a negative reflecting back. And then it hits here and it becomes positive again. And the cycle repeats. It just keeps bouncing back and forward unless I have any impedance to absorb the reflections. All right, I think I can do one last question, I guess. I guess got 10 minutes till 2. 1 or 2 more questions, I guess. Did that answer your question?
Yeah, that was fantastic. I think it was just a bit confusing with what we sort of needed to know, and then stuff was crossing over with EMAG.
So you'll need to know generally how to, like, if you have a transmission line, what the voltage is across that transmission line at a certain point of time.
Yep.
What the reflections might look like. If you have like sort of like worst case scenarios, to compute the actual matching coefficients, there are formulas. There's like
that was Rowell's stuff. Right?
Yeah, right. So you have Z. Oh, something like that, right? So you have. So say for example, you have a short circuit, right? Your system impedance is. Wait, did I get that right? Hold on.
I think it's the L comes first, and then
Yeah.
Z0.
Yeah.
But yeah.
Yeah. Braining it. Yeah. So if you have 0 ohms, that's minus 50 on 50. That gives you minus 1. If you have an open circuit, that's basically infinity on infinity. That gets you 1. Right? Yeah. So yeah, that's right. I should do that. Assuming, well, actually, no, not necessarily. It could be complex. Yeah. So generally, that's another good formula. Yeah, you might need to use that to find the reflection coefficient.
Sure.
But that's, again, this is sort of a bit out of the scope.
Well, we did cover those rho S and rho L, so they might crop up, I guess.
Maybe, yeah. So you have rho S. Okay, yeah, sure. You have rho S and rho L. So Z0 will be the impedance, the characteristic impedance of the transmission line. And
told to us, Julian? They just would say it has this impedance.
Yeah, so usually they say assume a system impedance of 50 ohms, which means Z0 will be 50 ohms, and ZL would either be the impedance looking into the generator or into the receiver, the load. Right, so you just look at either of those. And that's how you get your reflection coefficient. Usually you just assume it's a resistance, so you'll get some real number that's like, say, minus 0.3. Yep. And that's the amount that it will reflect back by, right? So say if it was a perfect open circuit, as I said, it would reflect by 1. If it was a short circuit, it would reflect by minus 1. So the amplitude would be 1, and the phase would be 180 degrees. You'd have 180 degrees phase shift of the of the signal, or in this case, it would invert it.
Anybody else?
There's no more questions from online.
Cool.
So
All right.
I might wrap it up. And
Yeah, all right.
chance
All
to get
good
to their
then.
workshop.
Yeah. Okay, cool. I guess that's it. Yeah, so my best advice for the actual quizzes, if you want to know, or if you don't, then whatever. Just do a lot of the practice quizzes. There's like 1 million of them out there. I think Tossin has from like 2011 to 2019 or 2021. Insane number. The only way of getting good at the quizzes is you just have to do them. You just have to do the quizzes. They're just it's like I think what Chris Hadfield, the Canadian astronomer, said. He said the way of training himself to fight against fear was, I think it was him. He would intentionally walk into spider webs. So you know when you walk into cobwebs, you're like, oh crap, oh cobweb, and you like dust it off. No, he intentionally would walk into cobwebs to train himself to not freak out. Just by like habit, just by walking into cobwebs. It's like, okay, it's nasty. I walk back, I get the cobwebs off, or I just deal with it, right? Training. It's all about training. Not memorizing, training. So that's the best thing you can do in terms of the quiz. Just subjecting yourself to a wide variety of the different questions and the different ways not different ways you'll phrase them, but the different styles of questions and whatnot, because it's very ad hoc. There's no formula to this. There's no like formulaic. Question 1 will probably be something to do with an op-amp. Question 2 will probably be something to do with digital logic or digital transmission, so transmission lines, digital logic, whatnot. Question 3 might be something to do with ESD. It could be something to do with PCB layout. It could be to do with decoupling. It could be to do with a whole bunch of other stuff. Who knows? That you'll just have that in there. Could be to do with noise. Who knows?
Well, thank you very much.
Yeah, no worries. All good. All right. I should probably stop the recording as well so we don't get 800 gigabytes.
Thank you for coming, everybody, and everyone online.